physical oceanography instrumentation, where we will try to, first of all, to learn what instrumentations are available on one hand side. On the other side, we should, based on what we have learned so far, the decision which kind of instrumentation we are going to use will depend on what kind of phenomena are we studying. And like 100 years ago, it was not so complicated because there was one single way to do the measurements, more or less, which are from shipboard measurements. But now the situation is much better that we have a multiple choice and in order to understand and see what kind of instrumentation to choose in order to study the specific phenomena. So that's the title. Here are a number of questions associated to this subject, which this is the structure of our lectures. The thing is why and how to observe study the oceans. Why, obviously, why to be able to first of all to understand what is the phenomena we are talking about. A second thing is not less important, is to predict. So we are doing trying finally to predict the phenomena or the evolution, temporal evolution of the phenomena. Physical oceanography observations are determined to research and societal needs, and are determined by types of platform and measurements. So these are two main criteria, two main base of criteria we are applying in order to decide what kind of measurement or observation do it. And then there is a third topic, which is observation with classical instruments. And this is the in our measurements. You remember this slide before. In our measurements, we have to take into consideration that the instrumentation, apart from covering a certain part of the ocean, having the certain resolution, whether we are going to measure the surface or in the water column, whether we want to resolve the large scale circulation, then in that case our spatial resolution could be very, very large. You don't have to be every kilometer in order to resolve the large scale resolution. You don't have to do the measurements very, very often if you want to resolve the large scale circulation. If you want to look only what is happening at the surface, you choose one specific type of instruments. If you want to, so this is one thing. The other thing is, however, is accuracy and precision of our instruments, because accuracy, which is the difference between the measured value and the true value, and precision is the difference among repeated measurements. These two criteria has to be satisfied in order to be able to do our measurements. And so if we know that the tides are on the order, the amplitude of tide is on the order of 10 meters, we don't have to have the precision of 1 centimeter, right? And so on accuracy, it doesn't have to be on the order of 1 centimeter. And so this is what we have to take into consideration. Therefore, before starting our measurements, we have to know what, again, as I was mentioning you before, you cannot start measurements, observations without knowing anything about the phenomena you are going to study. You have to have your knowledge before, or you have to have the hypothesis which is associated to the phenomena in order to decide how to measure and what will be the instrumental approach. Well, here is the something which is that physical oceanography is an experimental science, not completely, because it has its theoretical part, and if you consider numerical models as an experimental approach, so we have a double approach. One is direct observations, the other one is the numerical modeling. And however, physical oceanography as a very important part of the experiment of the physical oceanography is an experimental component and requires observations and exact measurements to achieve its aims. Okay. It can draw on the experience of the related science fields of physics and chemistry and make use of existing achievements in the area of technology and engineering, because the instrumentations are reflecting the state of technology in general, and the instrumentations, obviously that's an obvious thing. In 150 years ago, there were no electronic type of measurements. There were mainly the direct measurements, and yes, the manufacturers of oceanographic equipment serve as a small market but aim at selling their products worldwide. So the market associated to the oceanography obviously is very limited. We are talking about a certain number of oceanographic institutions or some specific organizations which are doing the oceanographic measurements. And here is, as I told you before, this lecture will give an overview of the range of instrumentation used at sea and the principles involved in this kind of instrumentations. And we will have, on one hand, the classical instrumentations, and on the other hand, the new modern development of this. And here's another thing what we have to see what are the available equipment and instrumentations. And we have the observing platforms. Observing platforms, we call platforms whatever is the structure on which the instrumentations are based on. So we have the research vessels, which are the oldest approach in oceanographic measurements. We have moorings. Moorings, they are fixed points where you put certain number of instrumentation in the put in the different depth. We have satellites which are measuring, as I told you before, which measure on whatever is happening at the surface. We have submersibles, towed vehicles, floats and drifters. Okay, so these are the observing platforms, because all these parts. First part presents a basis where we put the certain specific instrumentations to measure the temperature, salinity, chlorophyll, nutrients, and so forth. And another very important thing is the measurements of hydrographic properties. Mainly, so in the first place, which is hopefully very relatively simple, is the temperature, salinity. Temperature and salinity are the variables of state of the seawater, as we have seen before. Therefore, it determines the flow, determines the ocean currents from the geostrophic balance, as I showed you before. Then we have oxygen, nutrients, and the various other tracers. Oxygen, nutrients, they depend on the currents. Currents are partly dependent on the currents, because oxygen, for example, depends also on the production of oxygen or consumption of the oxygen in the water column. We know that the bacteria are consuming while the phytoplankton is producing the oxygen. The source of oxygen is the surface, And nutrients the source of nutrients are a river's coastal area, and even bottom is a source of nutrients. So these, the oxygen, nutrients, and various other traces we have, various other traces, they depend partly on the advection, on the transport by currents, and they are used also not only as the parameters themselves in biological studies or chemical studies, but they are used also as a complementary data to determine the circulation in the ocean. Because of the fact that they depend on the advection, on the transport, horizontal and vertical. To do these measurements, we have reversing thermometers. You will see later what are they. We have Nansen and Niskin bottles, which are the container, which are the bottles as the name says, which are used to pick up the samples at different depths. So with these Nansen and Niskin bottles at a certain depth, you pick up the samples, you take these samples to the surface and do your whatever is needed as far as the chemical analysis is concerned, determining the temperature, the oxygen, temperature, salinity, nutrients, and tracer, and so forth. So, but mainly oxygen, nutrients, and tracers are determined directly by chemical analysis. Then we have XBTs and CTDs. XBT means expandable bathythermograph, so that means that they are expandable, they're used only once and never lost in the sea. Then there is a CTD, conductivity, temperature, depth measurements. Then we have a multiple water sample devices. Thermosalinographs are the instruments which are typically installed on the ships, and they do the registration record of the temperature and salinity along the path of the ship. And then obviously there are remote sensors which are associated to satellites, but not only to satellites. You will see later that not only remote sensing is not only satellite based, but you can use airplanes, you can use also some coastal stations to measure currents and so forth, but you will talk about it later. And measurements of dynamic properties, this means currents, waves, sea level, and mixing processes. These measurements are done by current meters. Then we have wave measurements, instruments to measure the waves, to the high frequency oscillation of the sea level, which are on the order of 10 seconds. Because I haven't talked about the gravity waves. One of these themes, what I may suggest to you is to give an overview of the gravity waves, how to develop some formula associated to gravity waves. So the sea surface waves, which are mainly wind-induced, these are measured by specific instruments. Then we have tide gauges, where we measure the long waves, tidal wave. We have remote sensors, which are put on satellite or airplane, and then we have shear probes, which are determining the vertical profile of the velocity. There are different types of measurements. And we have direct measurements, which are measurements you have to be physically present at the sea, where you measure the temperature and the CTD and XBT, as I told you before. You can measure the currents by current meters. You can measure the current by floats and drifters. You will see later what is the difference between the measurements by current meters and by floats and drifters. Indirect methods are from satellites, from ADCP, that means the acoustic Doppler current profiler, which gives you the vertical profile of the current, so it doesn't do the measurements at a single depth, but gives you the vertical profile, which is very important. It gives you the shear, because the current is sheared, as you remember, due to the horizontal distribution, horizontal density gradient. Therefore, it's very important to measure the current shear. And then we have HF radars. High frequency radars are another remote method where you have the coastal stations and from these coastal stations you have the coverage of an area, and you measure surface currents. We will see later how these things functions. And then we have two types of measurements, two types of current measurements. One is Lagrangian, and the other one is Eulerian measurement. Eulerian measurements are done by current meters, research vessels, CDD, XBT moorings, and ADCP. So that means what we are doing is we are measuring at a fixed point. We are measuring at a fixed point, like doing the measurements of the wind. You have the anemometer, which is fixed at the roof of this building, for example, and it measures the current at this specific point. If you want to measure current by following the air or by following the current, then you do the Lagrangian measurement. Lagrangian measurements means that you put into the sea a passive body which follows simply the movement of water masses. And these are floats, profilers, and drifters. We will we'll talk about this in much more details. This is just the introductory part. And so this is the classical methods. We usually that's one of the research vessel, and it's seagoing ship has to be seaworthy and capable of riding out bad weather, and because you have to be able to do the measurements not with this kind of sea, but with the high waves. So there are limits. You cannot lose time to go to do your expedition waiting the weather, the sea conditions like this one. And so the ships have to be done like this. And requirement is that it has to handle heavy equipment, and the need for a large scientific part during the interdisciplinary study, because if you have the interdisciplinary study where it comprises biology, physics, and chemistry, then you have to have the personnel which follows different types of sampling. But not only that, it has to have the laboratories, equipped laboratories, where the people are able to do this kind of analysis. So typical ocean-going research vessel is 50 to 80 meter long, and it accommodates like 10 to 20 scientists, 20 or this large number of scientists due to the interdisciplinary studies. And then obviously you do work 24 hours, or 24 hours, so that means the whole day long. So you have to have also shifts. So this is the research vessel. This is the research vessel by our institute, OGS, Explora, which is mainly for the polar studies. And so in specific polar atmospheric conditions, then it's even worse than working in the Mediterranean. And so these are a number of pictures of OGS Explorer, which is a pretty old ship, and now I think within a few years we will be changing the ship into the new one. And the shape of the research vessel is determined by needs of what kind of experimental work we should do that. And large working, it has to have a large working deck, where there is you can see this is the winch, and by this winch you should be able to put into the sea a rather heavy equipment and take it out of the sea. And so the requirement to be at the sea for extensive period of time, because typically when the ship like Explorer it goes to Antarctica, it takes 6 months to stay there. So the ship has to be autonomous, not for 6 months, because it passed, but 4 months at least should be autonomous from various points of view, food and so forth. As you can see, 20 to 25 days, and sufficiently, it should be sufficient to operate at high seas within a few days of reach of land. Only the major oceanography institution in the world operate research vessels with global research capability. And as I showed you before, one of these first oceanographic cruises, which covered the entire globe, was a longer 1 year and a half or something, but obviously with the intermediate stops at harbors. But this is a very long period, and so not only from the point of view of autonomy, but also from the point of view of the collecting data. The data have to be collected, but then at the same time somehow stored in the ship in order to be and analyzed. For the first processing should be done on the ship in order not to lose time while coming back to the harbor or to the home institution. And here is the first instrument, because now we are talking about the measurements of hydrographic properties, temperature, salinity, oxygen, nutrients, and traces. And the first measurements, temperature measurements, were done by these what we call the reversing thermometers. That means that why is reversing? Because if you go with your thermometer at 2,000 meters, for example, you have to have the information on the temperature at that depth. If it measures there, and you bring your thermometer at the surface, it will change while you taking it out. It will change its temperature with respect to the original one when it measured at 1,000 meter depth. And so they invented this reversing thermometer, which is practically done in the way that it consists of a mercury-filled glass pipe, and the pipe is restricted to capillary width at the coil, so it's very thin at the coil. The instrument is lowered at the desired depth. Mercury from a reservoir at the bottom rises in proportion to the temperature, okay, to the outside, to the ambient temperature of the water. When the desired depth is reached, the thermometer is turned upside down. And what happens at this very narrow, very straight part, the flow of mercury is interrupted, so you got in a certain way frozen or registered that temperature at that specific depth. So you reverse the thermometer, and then you recorded the thermometer at that specific depth, and then you take out the thermometer and you read the temperature. This is one thing. The other thing is that at 1,000 meter depth, the pressure is 100 atmosphere. So therefore the glass is pressed by the pressure. Therefore we have to take into consideration that the temperature, the height of the mercury column is higher than it would be with the pressure 0. Therefore we have to correct this, we call it this virtual temperature due to the pressure. Therefore, there are two thermometers. One is covered, one is completely isolated by on the pressure, and then we do the differences between the protected reversing thermometer and the one unprotected. And these differences are simply due to the pressure. And we can also determine the pressure at which what the thermometer was there. So you have, on one hand, you have the temperature measurements, and on the other hand, you have also the pressure measurements, thanks to the fact that you have protected and unprotected reverse thermometer. When I was young, like you, I was doing the measurements with these reversing thermometers, and so you have to take them at 10 minutes to adjust to the ambient temperature. Then you send the messenger which makes it reverse, and then you take it out. So this is here. The reversing thermometer is thus also an instrument to measure depth, because depth is proportional to the density, to the pressure. And reversing pressure thermometers require a research vessel as platform and are used in conjunction with Nansen or Niskin bottles or multi-sample devices. You will see now what are these Niskin or Nansen bottles, what are used together with the reversing thermometers, which are fixed on these bottles. Oh, here is the figure. Here is the figure, more detailed figure of this reversing thermometer, and you have this part here, which is when it turns, the mercury column is cut, and then so you got the recorded real temperature. So this is the here, the green thermometer is an auxiliary thermometer which gives the ambient temperature. It is used to check the temperature when the main thermometer is red on deck. Because on the other hand, you have also another problem. When you come back to the surface, you have to read it as soon as possible. But obviously, you cannot read it immediately. Therefore, there are some influences of ambient temperature at the surface, and you have to correct it also for that. So on one hand you correct it for the pressure, and on the other hand you correct for the ambient temperature at the place where you read it. And the overall accuracy achieved by these reversing thermometer is 0.02, and you can also increase the accuracy to 0.01, which is very high accuracy. And you remember that this is the accuracy what really we need in order to record these small changes of temperature, both in time and space. So this is the reversing thermometer, and these are Nansen bottles. Nansen is the guy who invented these bottles. What is what they are fixed? They are fixed on a cable. You see they are fixed on a cable here, like this. And thermometer, this is these are the housing of the two thermometers, the protected and unprotected. And what is happening is, what you need is, you need this what is called messenger. If you have to send from the surface, you have to send along the cable. You have to send a weight which extracts this first part, and then all this thing is reversed, and then by that, not only that the thermometer is reversed, but also this thing is open. This Nansen bottle is open, and when it reaches the depth where you want to pick up the sample, you send the messenger, and turns and closes also this bottle. So you are guaranteed that you have a sample at a certain depth. You have the temperature and also the water sample at that specific depth. You see, this is how this inversion looks like. So this is the messenger which comes here, and then you can see this. But then there is another bottle below. The bottle below is opened by the other messenger. So you have the whole series of messengers which are opening the whole series of Nansen bottles, because you don't want to do measurements at a single depth. You want to do the measurements at 10, 12 depth. And you do it by a combination, by putting along the cable, put a whole series of Nansen bottles, which are opening at a given depth. It's very ingenious thing. And these are Niskin bottles, which are essentially the same. The previous one are metal. This one is plastic, and functions essentially the same thing. These are the coverage of the bottle, which once arrives this messenger, this thing closes, and so you have the sample at a given depth. You pick up, you go up, have a certain number of bottles, you pick up the sample, do the measurements of nutrients, of oxygen, of salinity also. At that time, the salinity used to be measured by chemical methods, by doing the titration and determining the chlorinity of the... Yes?
I really don't understand why it has to reverse.
Excuse me?
Why does it always have to reverse?
Well, it has to reverse because if you stay our thermometer stays at 1,000 meter depth. There the temperature is 5 degrees. Okay, and if you take it out by passing through different layers, it doesn't really have any more the temperature at 5,000 meters. It will have some kind of integral or whatever of temperature from 1,000 meters to the surface. Therefore, you are not really measuring the 1,000 meter depth temperature, but you are measuring something which is under the influence, the whole layer from 1,000 meters to the surface. So what you do is you invert this thermometer. You cut by inverting this. By inverting this, there is no more connection between the mercury column and the reservoir. So whatever mercury exits from the reservoir stays here, cannot come back. Okay? And so you are measuring that. This one, you can see this one, it doesn't have the mercury and doesn't have this thing, because it measures the temperature at the place where you are reading, doing your reading of the temperature at the surface. So it doesn't have to measure at the bottom or in the bottom column. It has to measure the temperature while you are reading this one, the pink temperature. Okay. Yeah.
So it means that the mercury and that liquid that cuts it off, are they in the same kind of container? Sorry, like in the same chamber? I should put, I mean, the mercury is, from the beginning, it's in, let's say, a ball. It's a unit. It's connected to the reservoir. Yeah. The reservoir. When you turn it, it's disconnected anymore, because this is the thing is very narrow. When you turn it, in that place, is disconnected. It's not that this is broken. It's simply disconnected. When you go back, put it on a real original position, the connection between the reservoir and the mercury is again established. Okay. Here it is. There are CTDs now. This is more modern type of measurements.
not they are not so ingenious solutions as inverting thermometers are, reversing thermometers are, but they are much more powerful in the sense that you can do the measurements not at 20, 30 meter depth differences. You can do the measurements in continuous. So you can see this is what appears when you do these measurements with CDD. What are you using here? You're using here the property that the water is there is a conductivity associated with salinity. There is a proportion. There is the direct proportion between salinity and conductivity of the water, of the seawater. Therefore, you are doing measuring conductivity, C. You are doing the measurements, the temperature measurements, T, sorry, and you are doing also the measurements of depth by measuring the pressure, essentially. Similar to what we have doing with reversing thermometers, where we are doing the measurements of the pressure and converting the pressure into the depth. So you are able with this thing to do the continuous temperature, salinity, and depth measurements, and you obtain at the surface and on your screen you obtain this continuous data, and then you do it, you see it in a real time. This is very important thing, and which is not possible with a reversing thermometer. These are the modern measurements from the shipboard measurements, and these are multiple samplers, which is not anymore a single bottle, but there are also typically 24 bottles put on this construction, and these bottles are used to pick up the samples, to pick up the water samples at different depth. So what has been doing is that there is a lowering of the structure at each depth. You stop, you close the one bottle, pick up the sample and go down, and then so you go turn around and do the, for example, you end up with having 24 samples. There is no continuous measurements of these parameters which are obtained from here, which are, for example, oxygen. You can have also the oxygen measurements continuously, but here you obtain the chemically analyzed oxygen, for example, on one hand, but you can also do taking the samples for determining the phytoplankton biomass, the zooplankton, small zooplankton biomass, and so forth. And so you can see that here still there are inverting thermometers. Why they are so? Because the CTD measurements, these has to be compared or calibrated with respect to the absolute values obtained from classical measurements. So you have a certain number of depth. You have the thermometer measurement, temperature measurement by thermometer, and then you obtain the calibration curve if necessary. Here, how they use pick up the samples from the bottles. The bottles are closed not anymore by messengers, by electronic way. So you close you close these bottles at a certain depth by pressing the button. So this is the multiple water sample device. And then we have a thermosalinograph, which is installed on the ship. And what it does is it pumps the water along the shipway, pumps the water into this instrument, where you have the continuous flow of the water pumped from the ship at the bottom of the ship, and then there is a continuous determination of the temperature and salinity along the ship track. And this is good because you have the continuous measurements, and but however it's only on a single depth, because this is installed at a certain depth at a certain point where the ship takes the water, and then you have the continuous measurements. And for example, they are installed on board of NOAA ships, but they are installed also on our ship Explorer. This is very good. And then there is XBTs. XBTs are expandable bathythermograph, which are instruments which has been used in oceanography for many years to obtain information on temperature structure of the ocean to depth up to 1,500 meters. This is a probe which is dropped from a ship and measures the temperature falls through the water. So it simply falls. It's a free fall of this probe, and two very small wires transmit the temperature data to the ship. So there is a very thin wire which transmits the signal from this probe. The probe is then designed to fall at a known rate. It is 1 meter per second. It has the rate, the velocity, vertical velocity of this thing, so that you can from the time you can infer the depth at which the probe was found, and then by plotting the temperature, the function of depth, the scientists can get a picture of the temperature profile in the water. After reaching the depth of 1,500 meters, the wire is broken, and then the probe is lost. So it's used only one. It's not a very good thing for the water pollution, obviously. But it's not used anymore so much. It was used very much by Marines, American, for example. They were using in their battleships to measure the temperature on the large scale in the Mediterranean, Atlantic, and so forth. We have had in like 20 years ago, we have had a big project where we have been using the XBT, rather intensive XBT program in the Mediterranean using commercial ships. So you pick up the commercial ship and then do the every 10 miles you do the measurements. Okay, this is without entering into details. This is the expandable bathythermograph. This is another thing, XBT. You can see how it's launched, and here is the guy, and it's connected to the computer in the lab. And here is the thin wire which follows the thing. The cost of this is like, it was used to be like, I think like $1,000 or something. Now we pass to current measurements. Current meters, ocean currents can be measured in two ways. When an instrument records the speed and direction of the current, or it can record the east, west, and north-south component, so which is equivalent. Both methods require directional information. All current meters therefore incorporate a magnetic compass. There are mechanical current meters which have the rotor like this one here, or a paddle wheel rotor, this thing here. There are different types of rotors. and can be designed to have a cosine response with the angle of incidence. And so these are the three mechanical type of rotors. I don't want to go into details too much. A long time ago, there was very interesting current meter mechanical, which is called Ekman current meter, which has the measure the obviously had a rotor, but then follows the direction. And how you register this movement, since it is mechanical, there was no registration, electronic registration. So you put it in at a certain depth, and it has a reservoir by number of small balls. And below that you have such plate where you have 1/16 of 360 degrees divided into 1/16, and then while this guy is turning, every 10 rotations leaves the ball, and leaves the ball at the place where the current meter is oriented. So you have, on one hand, you have number of balls are proportional to the velocity, and number of balls which are found in these parts gives you the prevailing direction. So it measures direction and speed, which is a wonderful solution. I was using this again 50 years ago or 40 years ago, and the biggest problem was the balls, because you know, if you do these measurements at 3 o'clock in the morning, if you lose the balls, you are lost. You cannot do the measurements anymore. So we went for the expedition with 2 kilos of small balls, you know, to make sure that we don't lose them. That's very nice thing. So the people were really genius in understanding, doing the in constructing this kind of instrumentation. These are much less. It's more sophisticated from the electronic point of view, but from the mental point of view, it's relatively straightforward. This is one of these very much used current meters, which are Dera current meters made in Norway. That's relatively cheap, costed like 10,000 euros, and so this is typically put on a certain depth, and it measures electronically. Records at the magnetic tape, recorded at magnetic tape, which is here inside, the velocity, and then when you pick up outside, and then you read your tape, and then you obtain the records. They are robust, reliable, and comparatively low cost. This is what I told you, like a 10,000, 20,000. You can attach to this, or it quite often has a temperature sensor, conductivity sensor, but also the chlorophyll, continuous chlorophyll measurements. So you can correlate the temperature, salinity, or chlorophyll measurements with the current, where it comes from. These are another type of measurement of current meters. These are electromagnetic current meters, and it practically measures the voltage resulting from the motion of a conductor, practically water velocity, through magnetic fields according to Faraday's law of electromagnetic induction, and so this is another type of instrument of the current meter measurements. We can go ahead. These are then again, acoustic. Then we have a acoustic meter, which is based on the principle that sound is a compression wave that travels with the medium. Then we have electromagnetic acoustic current meters, which have no moving parts, which is very, very useful, very good. Because if you have propellers, then after some time, due to the falling, you have to pick up the outside and then do the cleaning. Otherwise, it doesn't give you the real velocity. And then we have wave measurements. Wave measurements are well, for many reasons are rather important, because they can determine the destructions of the coast, coastal erosion, can help also in navigation, because if the ship wants to save on fuel, could be able also to choose the right route in order to avoid the areas where there is a strong wave motions. These waves, as I told you before, it depends on the wind, and there are rather good numerical models for reconstructing the wave field, the wind wave fields, and they are essentially, these consist of a float, of a buoy which stays at the surface and then follows simply the movement of the free surface and record these movements. And so you obtain from these instruments, you obtain the recording, wave recordings. There are quite important studies on wind waves, and I don't think we will do anything except if you want to show us the gravity wave solutions. And tide gauges, as we said before, tide gauges, they record tides, and they are practically done in this way, that you have the tower here, which is the steering well. The steering well, because you have to avoid the influence of the surface waves. You have to have only the vertical movement of the sea surface due to the tides, and not having any noise due to the surface wind waves. So it's connected with the open sea. There is here the how to say the body which follows up and down the sea surface, and then this is recorded, the paper used to be recorded at the paper, and so there is the analogous registration of the tides, which then can be digitized, used to be digitized once upon a time, and this is how it works. Motor steering well gauges are used non-mechanical means of measuring the water level in the well, acoustic or laser, and record the data electronic, but the principle remains the same. So this is the mechanical, but electronical essentially is done the same way. You may ask the question. You may pose the question about why do we need now anymore the tide gauges, since we have the very good measurements, sea level measurements from satellites. On one hand, there is a need to somehow to compare the in situ measurements with the satellites on one hand, which is less important, but more important is that at least so far, the altimetric measurements, the measurements of sea level, doesn't come close to the coast. So the validity, validity of the satellite measurements of the sea level comes up to 40, 50 kilometers from the coast. The whole, therefore, whole area close to the coast of the few tens of kilometers is not done very well by satellites. Therefore, the importance of tide gauges is still quite high. So this is the tide gauges are rather and then another thing which is also very important is that tide gauges are in function like for a few hundreds of years. Like the oldest tide gauge records are like 150 years, and this gives us important information of the sea level rise, right? Because the satellite records are from 1992, and if you compare this from 150 years of the measurements by tide gauges, then you can see how important is this. I might go back in one of these next hours to show you the real use of these tide gauges and their importance. Like for example in Venice, Lagoon of Venice, we have measured tide gauge measurements which were like 150 years. And these are very precious data which shows how strong is this sea level increase, or how important is subsidence of the land subsidence in the Lagoon of Venice, which is then causing the increase of frequency of floodings, because the whole sea level is relatively high, become higher and higher, and then number of floodings in Venice is increasing. And to know the sea level rate increase, the satellites are not so useful in specific locations. It's much more important to have tide gauges. Okay. So, yeah, here it says here, long-term changes in sea level linked with climate variability, because the sea level, I haven't talked about that. The sea level increases. This is the fact. It increases at a rate of about 1 to 2 millimeters per year. If it is connected to the anthropogenic influence, so that means that to the increase of temperature of the ocean, which is also another fact which has been recorded, but it's also connected to the reduction of the ice coverage over the northern, mainly over the northern pole areas. And these two phenomena are acting in the same direction, because on one hand the reduction of ice means the increase of the fresh water. We are adding the fresh water to the sea, so we are increasing the sea level on one hand. On the other hand, the increase of temperature makes that the water column is stretched, because the higher is the temperature, the higher is specific volume, or the lower is density. So, because of both reasons, which are presumably or probably consequences of the human activities, both are acting in the same direction. They are causing the increase of the sea level. In the case of Venice, there is another thing. There is a third thing which complicates this, used to complicate much more the situation. So on one hand, you have a global sea level increase, which is due to the sea level temperature increase and to the increase of the fresh water adding. On the other hand, however, in Venice, on mainland of Venice, there was a big industry, has used to be constructed in late 40s. This industry, what was using the water, the fresh water from under the soil, and this water was pumped out, and the result of that is the subsidence of the land subsidence in the area. So you have three processes, or two, maybe better to say two. One is the global sea level increase, and the other one is locally soil and the subsidence. Thanks to the fact that both in Venice and in Trieste here, we have two time gauges which have a time series of about 150 years. We were able to separate the two processes, the global sea level increase from the subsidence, because simply comparing the Trieste and Venice, in Trieste presumably there is no subsidence. The differences the difference between the two is due to the subsidence in Venice. And once this has been learned, the industry they didn't take any more the water. They stopped pumping the water from the underground, and the subsidence stopped. So now it's remained only the one component of the sea level increase, which is the global sea level increase in the Venice lagoon area. So this is how we can use, and how important as our tide gauge is, even though we have the satellite measurements. Okay, so that's always the same thing. This is just to this figure you have already been seen, and this is the first Challenger 1972-76. This ship, which has this departed in December 72 and returned in May 76. This is 4 years of a long oceanographic expedition covering the entire world with a resolution which was very poor, but there was some first understanding of some global ocean circulation, global ocean characteristic was coming from this that specific expedition. This was the chief scientist, was Sir Charles Wyville Thomson. Okay, so this is the introductory part, and this is the reference and reading sources. Here is the Emery and Thompson data acquisition and recording, oceanographic instrumentation from the Introduction to Physical Oceanography from Tomczak, what you have seen. And there is the third book, which is Instrumentation for Physical Oceanography, the last 2 decades and beyond, by Erickson. These are the reading material. I will leave to you the PowerPoint so you can copy this. And now we can start with the second lecture, and so that since we have time, and as I told to some of you, not all of you because you were not here, some of you were having the late coffee. By Monday I will send to you, if you send me your mail, I will make your mailing. I will make you the mailing list. I will send to you possible topics for your presentation at the day on exam. And now I will go to the second. Now the second lecture starts with autonomous systems, so the systems which do not need the direct presence of man, because on a ship we need the presence of personnel. At mooring, stowed vehicles, drifters and floats, autonomous underwater vehicles, gliders and autonomous submersible, it's not necessary the human presence. These are autonomous systems, and let's start with moorings, and then we will probably stop there. And the moorings, as I mentioned before, makes part of this Eulerian measurement. That means fixed point measurements, which consists of certain number of sensors and the anchor. There is a mooring line, wire or a rope, and one or more buoyancy elements, which keeps these instruments in the vertical, and this can be put at a chosen location for a longer time. We have, for example, in the southern Adriatic, we have the mooring system, which is there since 5, 6 years, and obviously you have to go there every now and then and take it out, control whether it functions, pick up the data if there is no real-time transmission. But this can stay as long as you want. Obviously you have to maintain the instruments because of the fouling and so forth. And for example, this specific structure, there are a number of recording current meters. You can see here. There is the ADCP acoustic Doppler current profiler. There are associated to these current meters. There is also the temperature, salinity, chlorophyll measurements, which are important, and oxygen if possible. Typically what you are also interested in for your mooring measurements, for your Eulerian measurements, is also to have the information on the meteorological parameters, on meteorological measurements. So what typically is connected to this or close to this another mooring, which is also only the surface mooring, which measures the atmospheric pressure, the wind, humidity, and all the meteorological parameters, so that you can see the response of the water column to the atmospheric forcing. You can see, for example, the ECMO response. If you have a very good wind measurements, then you can study the response. You can measure, you can find out the inertial oscillations, for example, which are which are able to, we were able to observe. The thing is that this not necessarily stays vertical, because it depends on currents. It can be sloped, it can be inclined, and so you don't really, you're not sure whether this is 2.5 kilometer depth, or it's less, or it's more. And so associated to these current meters, you have to have also the bottom measurements, the depth measurements. So you have the bottom, the pressure measurements there, so which you transfer into the depth and find out how these pressure changes, or how the depth of your instrument changes. How to choose the place where to put this oil area measurement. They have to be representative of the phenomena you want to study. If I want to study the vertical winter convection, so what I would do, I would study first. I would study first what is this is Adriatic. I would study first where this vertical convection is very likely to appear. So I have to know that the vertical winter convection appears at the depth, at the area where there is a cyclonic circulation. So I'm going to look for the cyclonic circulation if I'm sure that this process happens here. And if I find it here, for example, and this is where cyclonic circulation takes place in this concrete case of the Adriatic, then I put my mooring close to the center and try to find out by having the information on the water column and at the surface, finding the phenomena which appears, and trying to study the response of the water column to this kind of measurements. So that's another thing what I have to take into consideration, that I have to first define or identify the process I'm going to study. Second, once I identify this process, I have to know something about the process, to study the process itself. You remember the whole series of moorings, what has been put and maintained along the equator in order to study the progression of the Kelvin wave, equatorial Kelvin waves from east to west, bringing a signal. That has been done, studying and knowing what are the processes which they want to study or they want to observe. And those moorings were like this one here. They are having a certain number of current meters, having a certain number of temperature and salinity recordings, or even, but mainly concentrated in an upper part of the water column for the coastal upwelling, for El Nino phenomena. What is important is the first 1,000 meters of water column. So the measurements there should be concentrated in this area here. If we are going to study the vertical convection, then the measurements have to be done all the way down from the surface to the bottom. Obviously, the moorings are not enough to study a certain phenomena. We have to have also the other complementary observation. We have to have the satellite measurements. We have to have the temperatures, sea surface temperature measurements from satellites. We have to have the measurements of chlorophyll, because we have seen that chlorophyll is a good signal for the vertical convection. But we have to have also the altimetric measurements. Why altimetric measurements? Because altimetric measurements would give us the intensity of this cyclonic gyre, which is the center of the vertical convection. Because if you look from up, the sea surface in an area where there is a dense water formation, where is a cyclonic circulation, where is a cyclonic gyre. Yes, this is a cyclonic gyre. Okay. In the geostrophic, in the case of the geostrophic balance, here, what is the sea level will be higher here or here? In the case of cyclonic circulation. This is the cross section, right? So here the sea level will be lower, but the isothickness will be closer to the surface. And so by looking, combining the altimetric data with the mooring data, we can see to what extent the intensity of the cyclonic gyre contributes to the dense water formation, contributes to the vertical convection, apart from the meteorological conditions. The stronger is the wind. Yes?
The cyclonic movement is associated with the pressure, right?
Excuse me?
The cyclonic, so especially in the north, is
Low pressure in the surface.
And then convergence.
Yeah.
So shouldn't the surface be higher?
If the surface is high, this is anticyclone. And here is lower. Here is lower. Means that here the pressure is lower than here.
Okay.
Like in the atmosphere, you know.
I was thinking in terms of if it is lower, then there will be maybe convergence.
In this case, it will be divergence, because you see the water is escaping from the center, and then as a consequence of that, there will be the compensating upward flow, okay, which then deformates, cause the deformation of the isothickness toward up, and there is a loss of seawater from the center of these kind of structures. Okay, so this is how we determine the position or the location of the moorings in a function of the scientific goals what we have. We don't want to simply to observe wherever or whatever. We want to observe something in order to reach the scientific goal what we have. And the scientific goal is dictated by our interest, by interest of society or whatever, whoever. Okay. So there is another thing is what I have forgotten to tell you is at the bottom, because the question is how do I pick up these all these things from the ship, because at a certain moment I have to pick up this at the surface and do the maintenance of the instruments, and I have to pick it up by there is a remotely controllable release. So from the surface you send a signal, and then this release leaves is cut here, and then all these things goes to the surface. And then when all the structure is at the surface, then you simply go there and pick it up with the ship. So this thing remains there at the bottom. And then you have to, when you go back and put again the mooring, you have to have the weight put again there. So this is always very tricky operation because if you trigger the release, that doesn't mean that the release function, doesn't mean that the release down there function. So it might happen, it has happened quite a few times, that all these enormous quantity of data and quantity of instruments remains there at the graveyard. In order to minimize the loss of data, there is something which is called the real-time transmission of data. So all these current meters transmit the data in real time from the surface buoy, and therefore, at least even if the instruments were lost, the data were recovered and they are available for studies, which minimizes damage to the system. Okay, I think I will stop here.